All right, so in this section, we're moving on from trig. We're actually going back to polynomials, which we've seen before. We're just going to go through and talk about them more in depth and get a good definition for them. So in this section, you're going to be able to determine the end behavior, so what the graph looks like on the ends of a polynomial. You'll be able to identify zeros and multiplicities of zeros, and you'll be able to apply the intermediate value theorem. Okay, so let's talk about the end behavior of polynomials, and to do that, we're going to start talking about actual graphs, so the polynomials themselves. So here's the definition. I didn't realize I ran out of space here, but a polynomial function, we use the letter n to represent the number and the exponent. So n is a positive whole number, and so there's like a sequence of them. And they're real numbers where a sub n is not equal to 0, and it's a function defined this way. So basically, these are numbers, all right? This is the number n minus 1, the number a n minus 2. So basically, it's just like counting. This is the first coefficient, this is the second coefficient, third coefficient. And then here, these are the exponents. So n must be a positive whole number for us to have a polynomial. All right, so all of these powers should be positive whole numbers for it to work. All right, so I'll show you some examples. And we call this a polynomial function of degree n. So it tells us the degree here. All right, so let's look at this one. F of x is 5x squared plus 8x to the fourth, right? So notice that both of these numbers in the exponents are positive whole numbers. So this is a polynomial with degree. So the degree is just the highest power we have, degree 4. So this is an example of a polynomial with degree 4. Let's look at the next one. We have a fraction here, so that should give us pause, but first let's simplify to make sure things don't cancel. So I'm going to break this up into two pieces. So I get 1 plus 3 over x squared. 2 is a positive number. Does that make this a polynomial? Well, actually, do we remember that when we have an exponent on the bottom, we can move it to the top and make it negative? And this number is not positive, right? That's a negative number, so this is not a polynomial. Because the exponent we have here is not a positive whole number. All right, let's look at this one. 5, 4, 2. These are all positive whole numbers, so this is a polynomial. And then what's the highest power we have? It's the 5, so this is a polynomial with degree 5. All right, let's worry about this one. Can we have square roots in a polynomial? Well, what kind of exponent is that? Remember, when we have a square root, that means we're raising something to the 1/2 power. And when we have something in the denominator, we're making that power negative. And so x squared is good because that's a whole number, a whole positive number. However, this minus 1 up here is not good, and this 1/2 is not good, so this is not a polynomial. And so we've actually seen several cases of polynomials in our studies already, right? F of x equals 2. This is a polynomial. This is just the horizontal line at y equals 2. Oops, if I can draw it perfectly. F of x equals 2. This is a polynomial. This line that's slanted, right? 3x minus 1 looks something like this. I'm sorry, 3x plus 1. This is a polynomial. Also, we've seen quadratic functions. Quadratics are polynomials. It's a polynomial with degree 2. So that one looks something like this. polynomials. All right, so let's talk about the degree. So what is the highest power of this one? This one has degree 2. The highest power here, 1. So this one has degree 1. And then finally the highest power here, well, let's think about it. 2 is the same thing as 2x to the 0, right? Anything raised to the 0 is 1. So this has degree 0. All right, so all three of these are polynomials, and we can get even bigger with our exponents, and they're all polynomials. The only thing is polynomial functions of degree 2 or higher have graphs that are smooth and continuous. So for example, something that looks like this. It's continuous because I can follow it along without lifting up my pencil, and it's smooth. It doesn't have any sharp corners. Something like an absolute value. This is not smooth. So it's not a polynomial. Okay, so all in all, polynomial functions are functions we have worked with before. We just now have a name for them. And so what I want to talk about next is how to figure out the end behavior. Like, how do we know if it's going to go up or go down? And we have a test for that. It's called the leading coefficient test. All right, this is kind of small, but basically only things we need to look at is the very first term in our polynomial. So the highest power, the biggest power, and the coefficient in front. So this is how we compare these, or how we figure out what's happening. Okay, so if our exponent is an odd number, that means our ends are going to go in opposite directions. So this one, on one side it goes down and the other side it goes up, or one side it goes up and the other side it goes down. That's what happens when our power is odd. Right, and we've seen this before, right? Y equals x to the third. That power is odd. One side goes up, the other side goes down. Okay. If our power is an even number, both sides go in the same direction, both up or both down. And so we've seen this with quadratics, right? Both sides are either going to go up or both sides are going to either go down if we have an even exponent. Okay, and so the other thing we're going to figure out is how do we know what's going to go up and what is going to go down? And for that, we have to use the leading coefficient. So the number in front tells us things. So for example, if our power is an odd number and our leading coefficient is positive, that tells us that our graph is going to fall to the left and rise to the right. And if our leading coefficient is negative, we're going to rise to the left and fall to the right. Okay. Same thing with even, so both going in the same direction. If our leading coefficient is positive, they're both going to go up. And if our leading coefficient is negative, they're both going to go down. All right, so this one sounds more straightforward. This one you'll kind of have to remember what happens. All right, so we're about to do some examples using the leading term test to figure out the end behaviors. So what's happening? Are we going to go down to infinity or up to infinity with each of our functions?